I want to go back and pick up a topic from Lesson 6.4 that we just did not have time to cover when we were first going through Lesson 6.4. And this lesson will involve strictly graphing log functions. And I want to make a connection to something that we hopefully already understand and that we've already practiced quite a bit. And it relates the fact that log functions are inverses of exponential growth or decay functions. And what does it mean to be an inverse? Well, let's just take an example. Here I just went ahead and gave you an exponential growth function, y equals 3 to some power, and I went ahead and filled in the table of values using those same 5 domain numbers that we typically use. Well, since the log functions are inverses of these guys, remember to be an inverse, and if you want to find the table of values for the inverse, you just take these, in this case, this red set of ordered pairs, and you switch places with the xy coordinates. Okay, so that's true of any graph. If you want to find the inverse of a given graph, you can just take ordered pairs off of the original and switch the xy coordinates and you'll have the inverse. So pretty simple really. If you want to come up with the graph of a log function, just think of its related growth or decay function, come up with that table and then switch the ordered pairs for the log. Okay, so let me go ahead and show you the graph of this. This is that same table that I gave you on the previous slide. No reason to rewrite it. Let's just go ahead and graph these ordered pairs on our coordinate plane here. So here's 1, 0, here's 3, 1, 9, 2, 1/3, negative 1, 1/9, negative 2. Notice how now we're getting values closer and closer to the y-axis. And as we move to the right, as x values get more positive, we're going to continue to go upward. So here's the graph of y equals log base 3 of x. We're going to be approaching the y-axis forever. And we'll just keep going up as we move to the right. Okay, and I'll just go ahead and label this. All right, so a couple of things to take note of. You do not have to, first of all, when you do your homework, you don't have to show me the growth or decay graph in addition to the log graph. You just have to do the log graph. I just want to do it this one time just to make a connection again with the line y equals x, which serves as a reflection line between a graph and its inverse. And again, just wanted to show you how that's true. If you take corresponding points from each graph, like this red point here corresponds to blue, you see how they're the same distance away on either side. They're on either side of the green line, but they're the same distance. That would be true for any corresponding point that you wanted to find from the red and the blue. They're equidistant on either side. You could think of the word symmetry. It is like a symmetry line, and that's always true no matter what the graph is. When you graph an original and its inverse, there should be this line y equals x that serves as a reflector. You can think of it this way. If you picked up the red growth graph, pick it up, flip it over the green, and set it down, you would get the blue. If you can kind of visually think of that, pick it up, flip it over, set it down on the other side of green, and that's what the log function graph would look like. Okay, so now that we've had a taste of graphing one, let's try another one. This time we will start by building a table of values for decay. Y equals 1/4 raised to the x power. Okay, so we'll just start with this table and plug in, do inputs, outputs, 0, 1, 1, 1/4, 2, 1/16, and then when you go negative, you get +4, and negative 2, you get positive 16. Okay, well, that's not the table I want to graph. I want the log function graph. But remember, to get the log function graph, you just think of it as the inverse of this decay table. And to get the inverse, once again, I know I'm repeating myself, you just switch the xy coordinates. 1, 0, 1/4, 1, 1/16, 2, 4, negative 1, 16, negative 2. Okay, so I'm going to plot this table, and that will represent my answer. Obviously, I've got to be more worried about the x-axis getting big in this case. I've got to be able to plot 16, so I'm just going to turn these into units of 2, and I'll just leave the y-axis alone. All right, so let's plot these. 1, 0 would be right there. 1/4, 1. 1/16, 2, so we're getting closer and closer to the y-axis, this time as we go upward. And now 4, negative 1, and 16, I believe that's 8, 4, 5, 6, 7, yeah, this is 16, negative 2. Okay, so this is, once again, decay flipped over. All right, so that looks good, and let's just go ahead, just for sake of illustration, let's plot what the decay would look like so we could again see the relationship with y equals x. So here's 0, 1, 1, 1/4, 2, 1/16, getting closer, negative 1, 4, and negative 2, 16, which is way up here. All right, so decay does this. I'm approaching the x-axis forever. The log function does an approach to the y-axis forever. Can you see that? And now let's draw in y equals x, and we can again see the relationship. Okay, so it may be a little tough to see, but I have points, for example, I now didn't change the y-axis, so that throws us off a little bit, but this point corresponds to this one. This is supposed to be 1, this is 1, so again, you kind of have to remember the x-axis was changed. You can kind of get an idea of how the red and the blue reflect over the green line. Okay, this is going to approach x forever. This one is going to approach y forever. Okay, so again, don't want to make you think you got to do more than is necessary. All you need is the log function, which is here in blue. All right, so once again, get your table for, in this case, decay, switch the ordered pairs. Okay, let's try another one. All right, this time we'll start off with a table for decay, y equals 1/2 to the x power. I just took the base and made it the base for this exponent. Okay, 0, 1, 1, 1/2, 2, 1/4, negative 1, 2, negative 2, 4. It gives us a set of starting points. Okay, now let's go ahead and get the related log table. Put y equals here. All right, so to get the related log table, I'm just going to take those decay points again and switch them. 1, 0, 1/2, 1, 1/4, 2, 2, negative 1, 4, negative 2. Okay, so it's very important that you do that as a first step. After you've created your growth or decay table and you immediately switch those ordered pairs, now we're going to take care of these guys that represent transformation of this log. This is vertical compression, so we're going to take 1/4 and multiply times each of the y's. Then we're going to do the shift or the transfer. We're going to shift, after we multiply by 1/4 times the y's, we're going to move left 1, which is another way of saying subtract 1 from each x. And then we're going to move down 5, which is another way of saying subtract 5 from each y. Okay, so just going one step. I'm really done with this first table, this growth table, so I'll just mark it out. We don't need to look at that anymore. So let's take care of the vertical compression. All right, we'll just label that table. And that means 1/4 times each y coordinate. So I'm just going to write these x's down. Nothing's happening to them yet. But I'm going to multiply 1/4 times 0, 1 times 1/4, 2 times 1/4, -1 times 1/4, -2 times 1/4. Okay, now that's done. We're going to finish this up and we'll take care of these two movements in the same table. So I'll call this table left 1, L1, down 5. Left 1, down 5. So to accomplish left 1, okay, so you're basically done now with this table. Don't need it anymore. To accomplish left 1, we're going to subtract 1 from each of the x's. 1 minus 1, 1/2 minus 1, 1/4 minus 1, 2 minus 1, and 4 minus 1. All right, so that takes care of the left 1 shift. Now we're going to do the down 5 shift. So each of these y's, after I've done the compression, I'm going to subtract 5 from each y. 0 minus 5, 1/4 minus 5, 1/2 minus 5, -1/4 minus 5, -1/2 minus 5. Okay, and now we're ready to plot. These are the points, the final table points that I will use to come up with my graph answer. All right, so let's plot 0, -5, -1/2, -4 3/4. Okay, pretty far down there. -3/4, -4.5. It's pretty close, I guess. Okay, 1, -5 1/4. 3, -5 1/2. A little bit lower. Okay, so what's going to happen here, as you can tell, as I choose bigger numbers for x, I'm just going to keep on dipping lower and lower. But as I choose smaller numbers for x, I'm going to keep getting closer and closer to this vertical line, x equals -1. So you can tell by now what's inside the parentheses, what your vertical asymptote is going to be. So I'll try to connect these dots. So approaching x equals -1, you should not go past it. And then this is going to continue to gradually get lower and lower. All right, pretty rough, but it'll work. The big thing is making sure that your table is right so that this graph should represent the given table. All right, we're done with example number 3, and that's all I have. And so I just gave you 5 graphs that I want you to work on, and try your best with them. If you have any questions, let me know.